Welcome to the lesson on key performance indicators. Upon completion of this lesson, learners will be able to define key performance indicators, identify various types of KPIs to measure equipment performance, and identify common losses in collaborative robot operations applicable to EV manufacturing. Let us start by defining a key performance indicator, abbreviated as KPI. It is a measurable value used to assess the effectiveness and success of a process, activity, or system in achieving specific goals. When we consider the context of lean robotics, KPIs serve as quantifiable metrics that help track progress, identify issues, and drive continuous improvement. These metrics are essential tools that provide concrete data points to evaluate performance and guide decision-making processes. Think of KPIs as your organization's report card. They tell you exactly how well you're doing. These trackable metrics cut through opinions and guesswork to show the real picture of organizational performance. When you track KPIs, you're looking at hard numbers that matter for both today's operations and future planning. They're particularly useful because they let you break down complex processes into measurable parts, making it clear which areas are performing well and which ones need work. This way, instead of wondering how things are going, you have concrete data to guide your decisions. Here's a list of some of the best-known KPIs. They include manufacturing cycle time, cycles completed, utilization, efficiency, and downtime. One challenge when choosing KPIs is choosing only the KPIs that will help improve your process and add value to your process in particular. Now let's look at each one in detail. Manufacturing cycle time measures the complete production timeline from order initiation to final release, consisting of all manufacturing steps, quality checks, and processing times. Cycles completed indicates the robot's throughput capacity by measuring how many full production cycles it can achieve in a given time frame, helping managers assess productivity and plan production schedules effectively. Utilization examines the efficiency of robot deployment by comparing actual operational time to total available time, accounting for downtime, maintenance, and idle periods. The fourth KPI is efficiency. Efficiency measures how much of a robot's active runtime is spent on productive work during program execution, indicating the effectiveness of task programming and movement optimization. The fifth KPI, downtime, represents periods when the machine is not actively producing, which can occur due to maintenance, breakdowns, or scheduling gaps, and is typically tracked as a percentage to monitor overall equipment effectiveness. Let us now look at two layers of KPIs that are commonly used in an organization. They are strategic KPIs and operational KPIs. Together, these two KPIs create a complete picture. Strategic KPIs tell you if you're heading toward the right destination, while operational KPIs show you if you're moving at the right pace and performing well along the way. Strategic KPIs focus on measuring performance at a higher level of management and are aligned with long-term organizational goals. These KPIs provide insights into the overall direction and success of the business but are less useful for assessing machine-specific performance. On the other hand, operational KPIs are used to measure performance at a lower level, typically on the shop floor, and focus on day-to-day activities. These KPIs track the efficiency and effectiveness of specific processes and machines. Examples include overall equipment effectiveness, abbreviated as OEE, which measures the effectiveness of equipment and identifies areas for improvement in production, machine uptime, which tracks the amount of time machines are operational versus downtime, and product quality, which measures the defect rate and consistency of the final product. To summarize, strategic KPIs guide long-term planning, while operational KPIs help optimize daily operations and machine performance. Overall equipment effectiveness, abbreviated as OEE, is a critical metric used to evaluate the effectiveness of equipment in general manufacturing. It helps identify major losses and areas for improvement in production efficiency. OEE combines three key factors including availability, performance, and quality. Availability measures the amount of time the equipment is running versus the time it is planned to run. This highlights downtime issues. Performance evaluates how well the equipment performs compared to its maximum speed, identifying inefficiencies. Quality tracks the proportion of good products produced without defects, ensuring product consistency. While OEE focuses on major losses like unplanned downtime, slow performance, or defects, it may not always capture smaller, incremental improvements. These small changes, however, can still contribute significantly to increasing the overall effectiveness and performance of robotic systems over time. To understand how to improve equipment effectiveness, it's important to identify and address the common OEE losses, which can significantly impact overall productivity. Availability loss occurs during unplanned stops caused by equipment malfunctions, breakdowns, or other disruptions. These interruptions prevent the robot or machine from running during scheduled production time. Performance loss happens when there are small stops, for example, minor delays, or the equipment operates at a reduced speed compared to its optimal capacity. This reduces the overall output and efficiency of the robotic cell. Quality loss refers to products being rejected either during regular production or at the startup of the process. This can result from defects, poor alignment, or incorrect settings, leading to waste and rework. Let us now discuss the 10 common losses that are specific to collaborative robots applicable to EV manufacturing. To optimize robotic operations, it's essential to recognize these losses, as these inefficiencies can hinder overall performance and productivity. They are planned downtime, breakdowns, and unplanned downtime, minor stops, speed loss, production rejects, rejects on startups, integration faults, lack of use, inefficiency, and wait time. We will look at each of these losses in detail as we proceed through this lesson. Number 1. Planned downtime. Planned downtime refers to scheduled interruptions in operations for activities like preventative maintenance, tooling changeovers, or system upgrades to ensure the long-term reliability and adaptability of equipment. For example, in the EV industry, this includes reconfiguring robotic cells for new model year production. Number 2. Breakdowns and unplanned downtime. Breakdowns and unplanned downtime occur when machines stop functioning unexpectedly, often due to faults, wear and tear, or maintenance issues. These interruptions can halt production until the root cause is identified and resolved, leading to delays and potential losses in productivity. Number 3. Minor stops. Minor stops are brief interruptions in operations caused by quick issues such as misalignments, safety stops, or operator interventions. These are often triggered by maintenance activities, safety concerns, or adjustments to address minor deviations before they escalate into larger problems. Number 4. Speed loss. Speed loss occurs when a machine continues operating but at a reduced speed, often going unnoticed as an error. This can result from issues like equipment wear, suboptimal settings, or inefficiencies that impact overall productivity without fully stopping operations. Number 5. Production rejects. Production rejects occur when products are damaged, defective, or scrapped after a manufacturing process, leading to wasted materials and time. These issues can result from machine malfunctions, operator errors, or robotic handling mistakes, such as dropping or misplacing parts. Number 6. Rejects on startup. Rejects on startup refer to damaged or scrapped products that occur during the startup phase after a machine has been stopped or during a changeover. This often happens because parts inside the machine during downtime or restart processes may no longer meet quality standards or become unusable. Number 7. Integration faults. Integration or communication faults occur when errors disrupt the synchronization or data exchange between machines, leading to misaligned parts or halted operations. These faults often stem from software glitches, network issues, or improper configuration of robotic systems. Number 8. Lack of use. Lack of use happens when robots are underutilized or not operating at their full potential, often due to insufficient optimization or poor resource allocation. This results in wasted capacity and missed opportunities to maximize productivity and efficiency. Number 9. Inefficiency. Inefficiency or poor trajectory planning occurs when robots make unnecessary or irrational movements that reduce the overall efficiency of the system. For example, if a robot picks up a part and then moves in the wrong direction before reaching the correct location, it wastes time and energy, requiring adjustments to optimize the motion path. Number 10. Wait time. Wait time occurs when a robot pauses before continuing its operation, often due to non-ideal optimization or delays in the preceding machine process. This can happen if the prior task is running too slowly, causing the robot to wait for the necessary conditions to proceed, which reduces overall efficiency. Let us now look at our lesson summary on KPIs. KPIs are trackable objective metrics that focus on assessing organizational performance. They are critical for both current and future success, helping businesses evaluate various parts of their operations. The 5 best-known KPIs applicable to cobots are cycle time, cycles completed, utilization, efficiency, and downtime. Some common losses in cobot operations are minor stops, speed loss, and lack of use. To optimize robotic operations, it's essential to recognize the losses that can occur in cobot operations, as these inefficiencies can hinder overall performance and productivity. Thank you.